Okay, guys. So today there are 5 lessons in Unit 9, but lessons 1, 2, and 3 are really the big chunk of it, and then 4 and 5 is kind of putting everything together. So we are kind of finishing the big chunk of new stuff today. And we're looking at what is called residual plots. That's how you pronounce that word. Everybody say it with me. Residual plots. Okay? So what the heck is that? A residual is the distance between, so it's the distance between an observed data value and its predicted data value using the regression equation. So remember how on, I think it was 9.1, I had you guys, we were doing what was called interpolation, and you plugged in the value for the equation, and then you had to compare it to what the actual value was. Okay, and then you had to tell me if it was close or if it wasn't close. A residual is the difference between the observed, the actual value, and the predicted value. So now you're going to take the actual and the predicted, and you're going to subtract them, and that's your difference. Okay? So to do this, we're going to create a table to kind of help you organize your information. So I'll give you a second to set up the table, but here's kind of how it's laid out. On top of the table, I give you the linear regression equation. So this one is y equals 5.4x minus 134. And remember, the linear regression equation, what would be another word for it? Do you guys remember? Line of best fit. Okay? Okay, so linear regression equation is just the same as saying a line of best fit. Here's the equation. And this is measuring distance or speed and braking distance. So braking distance is like when you're driving, your speed affects how far you go when you brake. So say you're driving on the freeway and you hit the brakes, it's going to take you longer to stop because you're going faster. Does that make sense? Than when you're driving down the regular street and you're driving really slowly. So this is telling you the speed and how long it takes you to brake, and then we're going to fill out the rest of the chart. So these are the speed that's given. This is the observed braking distance, so the actual distance. And then we're going to, in the third column, use the linear regression equation to find the predicted braking distance based on the equation. And then in the last column, we're going to find the residual value, which is the actual value minus the predicted. Okay? Okay, guys, so to find our predicted braking distance, we're going to take our speed, which is our x value, and plug it into the linear regression equation. So the second column, like I said, is the actual distance. So somebody stood outside and measured it. And then we want to use the linear regression equation to predict it. So this is going to be 5.4 times x. X is your speed. So what's the speed in the first row? 30. So times 30 minus 134. And that should all come out to 5.4 times 30 equals 162 minus 134, 28. Okay? So what I want you guys to do is finish that for all of the other speeds. So do the predicted braking distance for all of the other speeds for me. Okay? All right, guys. What did you get as the predicted braking distance for 40 miles per hour? 82. Okay. What about 50? 136. What about 60? 190. What about 70? 244. And what about 80? 298. Okay. Some of these are close, and some of them are not so close, right? Which ones are not so close? The 136 and the 120. What about this one? 48 and 28. And then what would the other one be? 320 and 290. Yeah, they're not so close. So what we're going to do next is we're going to calculate the residual value. Residual value, remember, is the difference between the predicted and the actual. Okay? So we are going to subtract the predicted and the actual. So, or I'm sorry, the actual and the predicted. So residual value for 30, we're going to subtract 48 minus 28. And the order does matter. So observed value always comes first. Predicted value always comes second. Okay? So 48 minus 28 is going to give me a residual value of 20. So do that for all of the rest of the speeds. Okay, guys, what did you get for the residual value for 40 miles per hour? -2. What about 50? Okay. What about 60? -10. 70? -4. And 80. Okay, how many residual values came out to be positive? How many came out negative? 4. Okay. So let's talk about what this means then. So do you think, looking at our observed distance and our braking distance, or our predicted, sorry, or our residual values, do you think this is a good line of best fit? Why not? Yeah, it doesn't work with everything. Negative doesn't necessarily mean a bad thing, but there's a big difference between 20, 22, and then like -2 and -4, right? The difference, or the distance, means that these two values are pretty close. These two values are pretty close. I would even say that these two are pretty close. But then we have some that are 20 points apart, 22 points apart. This one is 16 points apart. So probably this is not a great line of best fit. So what we can do then is we can take these residual values and plot them, and that will kind of tell us if our data points are even making a linear sort of shape. So one reason why some of our residual values might be, or some of our predicted values are close where others are not, is because maybe if we were to plot the data, it doesn't actually come out very linear. So we can plot our residual values to determine whether or not our graph is even making a linear shape. Okay? So a residual plot. Let me zoom out. A residual plot is a scatter plot of the independent variable on the x-axis and the residuals on the y-axis. Okay? So it's going to be a scatter plot. Your independent variable is on the x-axis. That's going to be like the speed that we plugged in, so what we plugged in for x. And the residual values, so the very last column, is going to be on the y-axis. And then here's going to be how we set up our residual plot. So a lot of residual plots have your y-axis is going up and down, and your x-axis on a lot of them go down the middle, because we're going to have some positive values and some negative values. Okay. So your x-axis is the residual, or your x-axis is the speed, what we plugged in, and your residual value is going to be on the y-axis. So that's going to be the final column of the chart that we made. Okay, so let's graph these things. So remember, the x-axis is going to be your speed. So the first speed that we have measured is 30. So we're going to start along the x-axis at 30. What was the residual value for 30, guys? 20, right? It's the last column on our chart. So my x-axis, I'm going to be at 30, and my y-axis, I'm going to go up to 20. So you're going to put a point there. Okay. My next speed that's given to me is 40, and the residual value is -2. Now, my graph is going by 5 in this case, so -2 is going to be somewhere in between 0 and -5. So somewhere in the middle at 40. So I'm going to put it right here. Okay. So what I want you guys to do in your groups is finish plotting the rest of the residual values, and then we'll compare it with what I get. Okay, guys. So the next x value was 50, and the residual value was -16. So that's going to be like just below -15. So you should have got a point right there. And then the next one was 60 and negative 10. So we're going to be right on again. 70 and negative 4. So that's going to be just above negative 5. And the last one would have been 80 and positive 22. So that's going to be somewhere right here. Is that what your guys' scatter plots look like? Okay, now this is a scatter plot. So do we want to connect all the points? No. So you're just going to leave it like this, okay? So let's take a look at another reminder that I want to give you guys is on your homework, you will be given this kind of idea, but it'll be blank, so you'll have to decide the interval. So is it better to count by ones? Is it better to count by fives based on the points that they give you and the points that you get? It is okay to estimate because some of the residual values, for example, we were able to count by fives, but some of them fell in between. So just give me your best estimate because we're really just looking at the shape. So let's look at the scatter plot and the residual values. When do the residuals have positive values? When they're further up. Yeah, this is 0, right? So then we have when the actual value. So let's think about what our actual value was and what our predicted value was. What did you guys notice? So for our two that have positive, what do you guys notice about the actual value and the predicted values?
See, it goes like from bigger to like every gets.
Which one is bigger here? The observed or the predicted? The observed, and our residual came out positive, right? Which one was bigger here? The observed. So how would we get negative values then?
Because it's going like this.
When the predicted is bigger, and then when we look at the scatter plot, all of those are below the x-axis, right? Okay, good. So now let's talk about how we would use this to interpret the data, okay? So how would we use the shape of the residual in order to interpret the data? First thing that you need to know is if there is no identifiable pattern or a flat pattern, so we're looking at no identifiable pattern at all, or if we get a flat pattern, then the data may be linearly related. So when we look at the residual values, or even if I just give you a residual plot, if we see a pattern, or if the residual plot comes out flat, then if we look at our data, it might be a linear kind of set of data, okay? And so here's what I mean by a pattern, no pattern, or flat, okay? So here's two examples. This first one has no pattern because they're all of the residual data are just totally all over the place, okay? So there's no pattern at all. This is what's considered a flat pattern in the plot. All of our positive values kind of make a flat sort of line, and all of our negative values make a flat sort of line, okay? So when do you guys think the residual plot would give us indicate that we do not have a linear pattern? Yeah. So if there is a pattern, so there is definitely a pattern in your residual plot, then the data may not be linearly related. So here's two examples, okay? So if we look at this first example, do you guys kind of see a pattern? It sort of looks like a sideways Y. These beta values are kind of going up, and these ones are kind of going down. So it kind of has an increasing and a decreasing pattern. Or in the second one, the pattern's even more identifiable. It almost looks like an upside-down parabola, right? So there are two examples of what a pattern looks like, and then they're described down here. On this one, as the x value increases, they become more spread out. So they either get higher or get lower. On this one, has more of a curved pattern. Okay, so two examples of what a pattern in the residual plot might look like. And that means that our data would not have a linear relation, which means a line of best fit is not appropriate for that set of data. Okay, guys, so looking back at the residual plot that we just made, this guy, in example 1. Does this have a pattern, yes or no, first of all? Yeah. No, remember what our no pattern looks like. No pattern means a whole bunch of data points totally all over the place, kind of like you just put a bunch of dots all over the place. Does this one look like it has kind of a pattern? Yeah, it kind of looks like a parabola, right? It goes down and then starts to increase. So do you think that this set of data that we looked at has a linear relation? No. Remember, if we had a pattern, because we gave you one that looked like this, which was just upside down of what we had before, it does not have a linear relation, meaning if we were to graph our data, it might look like an exponential, it might look like a parabola or a quadratic, it might look like something totally different. But if we were to plot the data that I gave you right here with the actual observed distance, it wouldn't be linear. So a line of best fit would not be appropriate, okay? So what I want you guys to write that underneath right here. So just underneath right here, a linear regression may not be appropriate, okay? Or a linear model may not be appropriate. So let's write that. So a linear model, meaning a linear line of best fit, for this data set. Okay? So because we have kind of a pattern, that tells us that the actual data doesn't really look linear. So a line of best fit isn't really appropriate for this set of data because our predicted values, some of them were way different than our actual values. Does that make sense? Okay. So the last thing that we are going to look at is when I give you actual data and the residual plot and the linear regression equation, we're going to kind of analyze it and decide if a linear model is the best way to go. So I am going to have you guys write this in your notes so that you have one example. It shouldn't take you that long to write down. Your plots can just be good estimates, okay? So it doesn't have to be exactly like this. But I do want you to write the linear regression equation, the chart of the data, the scatter plot, and the residual plot. Okay, guys, so let's look at this example of data. We have our linear regression equation that they give us. It's y equals 3.93x minus 11.33. So remember, that's our line of best fit for this set of data that's given. They also give us the R value. R is 0.8241. That, remember, tells you how tight your data is in a line. So how close is my line of best fit to the data point? And then I give you the actual data points right here. This chart right here is the scatter plot and line of best fit of the data points. And then this one right here is the residual plot. So I give you basically like everything that we've been working with so far. So let's look at all of the different pieces. First of all, let's look at the data, x's and y's. My x's go up by 2s, 2, 4, 6, 8, 10, 12. And then what do you guys notice about the y's? Kind of random. This one's a 9, and then it goes down to a 2, and then it goes down to a 1. So what's happening from 2 to 6? They're decreasing. And then what's happening from 6 to 12? It's increasing. So just looking at the x and y values, do you think that the data looks linear? No. I'm not thinking so right now. And then look at your R value, 0.8. Is that high? High, remember, means close to 1. Kind of. So our R value tells us that the line of best fit is pretty close to everything. And look at the scatter plot. Here's my data points, that are from the chart, and then here's my line of best fit. That's this thing right here. Okay, remember the residual value, or I'm sorry, the regression equation. So does it look like my line of best fit is pretty close to my data points? Kind of, right? It's close to most of them except for this one, and that one, right? So it's kind of close. My R value says that it's pretty high, but when we look at the residual, what do you guys notice about the residual plot? It definitely has a pattern. So do you think that a linear model is appropriate for this set of data? No. So I want you to write that. A linear model is not appropriate for this data set. Okay, and by appropriate, I mean a good fit, not inappropriate, like naughty, okay? I mean appropriate, like it's a good model. But you guys, because look, if I were to actually connect all of my scatter plot points, now it's a scatter plot, so we're technically not supposed to do this, but if I were to connect them, what kind of shape does it kind of make? Like, let's say I keep going up this way. It kind of looks like a quadratic, right? Is it linear then? Probably not, okay? So what you are going to be asked to do is you will be given all of this information, and I do want you to look at all of the information, because sometimes if we just look at the correlation coefficient, we might think that our line of best fit is pretty good, because 0.8 is pretty high. But if we were to look at the scatter plot and the actual line of best fit, it's pretty close. But if we look at the residual plot, it definitely has a pattern, right? So a linear model will not be the best method. So we have started looking at all of these pieces individually, and now when we put all of these individual pieces together, the actual scatter plot, the linear regression, so your line of best fit, and the R value, so how close is my line of best fit, and now the residuals, we can get a really good picture of what shape our data makes and if it has a linear relationship. Okay, so now we're going to be taking, for the rest of the unit, all of the parts and putting them together to determine if we have a linear relationship. Okay.